All right, so today we're going to go over thermal inversion as we prepare for our thermal inversion lab. So first, what is thermal inversion? So thermal inversion is where there is a warm layer of air and it is trapping the cool air beneath it. It is also trapping any sort of pollutants. Those pollutants normally disperse into the air higher up, but this warmer air layer is going to serve as a lid. What is causing it is at nighttime, the ground cools much faster, and so that warm air is trapped while that cold air is beneath it. So what normally happens to air temperature as altitude increases is that air temperature is going to decrease because there's less atmospheric pressure. So this cooler, as we go up, there's cooler air, but what happens especially when there is the heat rises, as you know, and so as it goes, it's not going all the way up as it typically would, and so that cold air is trapped. So in thermal inversions, we're not going to have normal atmospheric conditions where that warmer air goes up and disperses. The surface is going to be warmed by the sun, and when it cools, the air would typically go up. So during a thermal inversion, that cool air is trapped under a layer of warm air. The warm air during a thermal inversion is going to sit on top of that cooler, denser air and serve as a lid. And this can become a problem because pollutants become trapped during these thermal inversions because they can't rise and dissipate like they typically would. So typically, normal conditions, the surface would be warmed by the sun, and so the air increases, and those pollutants would be carried up, and they would be vertically mixing, and so they would be spreading out throughout the atmosphere. But here we have in a thermal inversion, that cold air is trapped, and so those pollutants are going to hit that inversion layer and they're going to come right back down. We see this often in cities like Los Angeles, where there's smog. It's basically just the pollutants are trapped beneath that warm layer and they can't go up. So some situations that are going to lead to thermal inversions are going to be warm fronts, where the air is typically warmer than normal. It also can be very prone to happen in valleys, because in valleys that dense air is going to sink from the slopes and that cold air is going to go down into the valley, and that warmer air is going to be left up top and it's just going to hit a lid on top of that. That can also be why we see a lot of fog in valleys. So thermal inversions occur more often at night because the Earth's surface is rapidly losing the heat after sunset and it's cooling that air. And basically the air cannot keep up with how fast it is going to be cooling down. So they're also more common in winter because the radiation from the Earth exceeds radiation received from the sun. So at nighttime, with the Earth has trapped all that heat during the day, right? And so it's releasing that heat up into the air. And at night, the ground is cool, but the air is hot. And so that heat rises, but we're not getting enough to replace that. The presentation also mentions oceanic upwelling areas like California, and that is going to contribute to inversions because the cool air from the ocean winds, like we talked about when we did El Nino, is going to cool the surface while the warmer air is still going to act as a lid. So when the surface gets cooled faster than the air can dissipate, we get a warm layer of air as a lid. So during a thermal inversion, the air quality, right back here, we see this layer of smog. So air quality decreases drastically during a thermal inversion. All of those pollutants are trapped in the air directly into our breathing. So it's going to impact human health. We're going to have higher levels of breathing issues, asthma, bronchitis, things like those. Anything where pollutants is going to affect how we breathe. It also impacts plant life because one, it's going to affect how much sun those plants can get. So that's going to directly impact the rate of photosynthesis. But it's also going to cause it harder for them to absorb water because those pollutants are trapped, and they're also getting trapped into the waterways. Cities experience worse effects from thermal islands because cities are essentially what we call an urban heat island. So, urban, obviously cities, heat island just means they are a smaller area where around them might be cooler, but the city itself is going to be hot because the concrete and the buildings absorb that heat all day long. And then this trapped heat is going to create a dome of warm air around the city. So you might notice sometimes where it's not as noticeable in Texarkana, but it is slightly noticeable, where in Texarkana it might be a few degrees warmer than it is directly outside of Texarkana because we have concrete and roads and buildings that are trapping all of that heat because they're darker, right? And then we go outside of Texarkana and we have all this ground, this grass that is going to be cooling the air. So we have this urban heat island. So what you're going to do next is, based on what you've learned, what conditions would you try to create in a model to simulate a thermal inversion? How can you show how the cold and the hot might cause some sort of trapping or things like that? All right, good job.